After that, we'll talk about some of the goals and constraints that we have for our project. And after that, we'll talk about how we analyze Dordt's current system and then use the data from that analysis to design a new system. Finally, we'll talk about a proof of concept by telling you how our demonstration works. So first we're going to go to Philip Topp, who's on channel 54.
Greetings, welcome to the agricultural surgery room in the basement of the science building. We chose this room as part of our demo because it is a small room with specialized use. This will be used in an example of where you have a lot of people and you can show this in a larger classroom or over the network as part of a distance education course. I'd like to give you a brief overview of cable systems before we begin. There are two main types of cable systems, one-way and two-way systems, and these consist of two main parts, that of the head end and that of the distribution system. But to show you what these mean, I'd like to give you a diagram. This is an example of a one-way cable system. There are two parts, the head end and the distribution system. The head end consists of multiple programming sources. These would be such things as satellite channels, television stations, or informational channels. These are all combined onto the line and distributed to all the different receiving sources. In contrast to this is a two-way system. In form, it's very similar to a one-way system, except for one very important difference. That is, the sources can be anywhere on the system. They do not all have to be on the head end. This would allow for programming in various locations. To do this, the signals travel in both directions on one cable at the same time. Now let me describe a little about Dordt's current system. Within the classroom and science buildings, the existing system has been extended beyond its capabilities. Channels have been added that were not planned in the original specifications, and it also has been expanded for what the network is capable. Thus, the channels on the lower frequencies are received well, but upper channels are not. There are also, in the broader campus, there's also multiple entry points onto the campus. This prevents Dordt from having one centralized location where we can feed video, programmable text generators, and information channels containing such things as the day or other channels that would benefit the Dordt community. In the campus, there are also no permanent two-way paths. That would allow people to do what we're doing today. In light of this, we set some goals for our project. The first is to improve the quality of the system. The second is to increase the potential uses of such a system for a wide range of applications of current and future uses. The third is to facilitate the development of distance education on Dordt's campus. We also set some constraints for our project. The first was ease of use. We wanted the system to be able to be used by anyone on campus easily, and also to have it be easy to maintain. Another constraint is to maintain the existing relationships Dordt has with the community. The third is a high standard of quality, both in the design and functioning of our cable system. To begin describing how we went about doing this, let's go to Nick live from the BJ Hahn Auditorium from Channel 64.
Thank you, Phil. I'm here in the balcony of BJ Hahn. You can see behind me, there's the organ. I am actually in Jim and Rye's office. And this gives us a chance in the BJ Hahn to film things such as, we've got choir concerts and graduation that we might want to bring about through the cable system. I'm going to talk about how we analyze the current cable system. And for an accurate model of our current cable system, we needed to know about all the components that were in this current cable system and their specifications. We started out at the head end of the system and went through the whole system, finding out all the different types of cables, amplifiers, splitters, and taps that were throughout the system. And we drew a diagram of that. We also needed all the distances and lengths that were between all these components. In order to properly measure this, we needed to use the network analyzer. This is the piece of equipment that you'll see in S101 next to Brian. This allows us to pick a frequency range, and it will give us the power output. So we can choose a channel and go into its range, and we'll be able to see the power output of that channel. This allowed us to model the system, and we were able to put these into a LabVIEW program. LabVIEW is a type of computer language that we were able to use, and it made it so that we could analyze the whole cable spectrum. And if you look at the graph on the next slide, you'll see this is an example of one of the LabVIEW simulations. You can see our own measurements and the model that LabVIEW gave us. If you look on the x-axis of the graph, you can see that the frequency is in megahertz, and this is the range from about 100, which corresponds close to channel 2 or 3, and to 400, 500, which is close to channel 50 in our cable system. You also see how our graph and the measured one are pretty close throughout most of the higher ranges, but you'll see that there's a slant from the low channels 2 and 3 to channels 50. It slants down to about the negative 20 dB mark, and this is a sign that there's tilt in the cable system. We're now going to go back to Brian, who's an S101, and he's going to discuss how we designed the new system.
Thanks, Nick. A couple things I want to talk about for our redesign. First of all, I want to explain to you how a head-end works. The head-end, as Philip showed us on the diagram, is the origination point where all the channels start. And there's a couple ways that we can get channels. The programming is what we call the channel lineup, what channels you have. And there's different sources you can have. A common one is to have a satellite system with many satellite receivers. And all these satellite receivers will go to modulators on their own channel and turn on the system. This is a good way if someone wants to pick out exactly what channels they want on their system, because they can decide what channels they'll have. Another option would be to take the cable signal from the local cable company, Premier Cable, and simply send that down the line at our head-end. That would allow us to use pre-existing modulated signals from the cable company and then insert in our own trouble-free. The benefit to this is that we can maintain the community relationship with the cable company that we already have, according to one of our constraints, and the price of the program is pretty competitive, so that's a good way to go. So we recommend that for our design system. Another option that comes with the head-end is the idea of local origination, which means that we can have our own channels, and if we can get the signal to the head-end via something like a two-way cable system, we can insert the signal and it can be distributed to the whole system. That would be local origination. And finally, we had to decide where we want the head-end to be. And that we decided to go in the media center because they would most likely be in charge of the system, and they would be able to maintain the programming and the local origination channels. Next, I'll talk a little bit about the system design. System design is fairly standard for the layout. This is a diagram of our design. Up here we have the head-end system in the classroom building. And from the head-end, the signal gets distributed to the different buildings via fiber optics. That's the green lines here. Once it reaches the building, it goes into an amplifier, that's the red triangle, and then through a splitter network. And from the splitter network, the signals will travel on coax to each individual room. So the layout wasn't too hard to design, we just had to make sure we had enough splitters in every building and so forth. The hard part is figuring out what gain the amplifier should have and how much tilt we should add to it to compensate for signal loss in the wire. And to do that, we used our computer model that we had originally made, and we built our proposed system in the computer model. And with that model, we were able to adjust all those variables until the output signal was as good as we could get it. And once we had that model built, we took an opportunity to compare the new system to the current system on Dort's campus. This diagram here will show that we gave our model an input signal of 0 dB all the way across. This means that every single channel is getting the same amount of power. And that's what you want. You want all the channels to be the same. You don't want some to be weak and some to be strong. Well, up here we can see the output of the current cable system in the classroom building. And you can see that tilt that Nick was talking about. In fact, the usable range for our cable system in the classroom building stops around 300 hertz, which that's about negative 20. And that corresponds to approximately channel 13. So the system in the classroom building is up to spec up to about channel 13 or so. In contrast, here's a diagram of our proposed system. We gave it the same 0 dB input spectrum. And the output you can see is an almost perfectly straight line all the way up to over 700 megahertz. And 700 megahertz corresponds to the entire frequency spectrum that the cable signal from here would be, plus many more. So next we're going to go to Howard on channel 66, and he's going to talk about how we got this little demonstration working. Howard?
Yes, Brian, I'm located in the Media Center, and this is where our head end is here at Dordt College. We actually receive the signal from Premier Cable, but with the rest of the equipment here behind me, we actually can switch different signals onto the cable system that can be sent to the different classrooms for special events that are going on, or special channels that are viewed for certain classes. Also, right behind me, since I'm here in the head end, I have pictures of all the other ones, everyone else you've been seeing so far. Right now we have Nick Hookman in the BJ Hunt, able to see in the monitor. He's in that one, and this other monitor behind me here, we have Philip Top, who's located in the surgery room down in the biology area in the science building. And then this third monitor has actually a picture of what you're seeing in S101. We have a camera in the room there so that everyone else can see what's going on. And the fourth monitor is just showing a picture that you're watching of me. And so what I'd like to talk about a little bit is our proof of concept and how we went about doing the demonstration for you tonight. When we were considering how to do the proof of concept, we decided that we wanted to do our presentation from a few remote locations rather than doing the entire thing in the room. And by doing that, we could prove the two-way capabilities of the system as well as do our presentation at the same time. And to do that, we thought, well, we could implement part of our system, and that way it would give extra capabilities to the system and also allow us to demonstrate that. The problem is that the equipment to actually implement it as we had designed is very expensive. It utilizes the low-frequency channels, which have very low loss, but that equipment is very specialized and also very expensive for both transmitting and receiving. So we went to a second idea, and that was to get very high-frequency or high-channel modulators that are in very high frequencies. However, those get a lot of loss in the system, as I was showing you earlier, because of the tilt. So to overcome that, we had to run a number of tests. We were within our price range with those modulators, but we needed to make them work on the system. So we tested them on the system, and as our model showed, we needed to add a lot of amplification to get those signals up through the system, and we were able to do that. In the process of performing those tests, we also found that we needed a way to receive the signals off of the cable when it got back to the head end. And the reason that was a problem is because at the head end, the rest of the signals in the lower channels are very strong, and it will actually overload the tuner and the receiving equipment on the head end for those feedback channels that are coming back up. So to work through that problem, we designed a filter, and we designed specifically a high-pass filter to do that. So if we move to the next slide, it'll show you some things from the filter that we designed. There's a number of things going on in this slide. If you look at the right half of this slide, you'll see that the line is very high. And what that indicates is that those high-frequency channels are going to be allowed to pass through without attenuation. Compared to the left half of the slide, the line is very low, showing that those low-frequency channels will be attenuated or suppressed through the filter. Also, the very, very wide green line that's on there is a line representing how well the filter we actually designed did when we tested it out, whereas the other band of color that's behind it is a computer representation of how well the filter would have worked if we actually did build it. So this slide shows us that the filter we actually built did work very close to as well as we had designed it to work. And that filter, along with the other tests that we ran, allowed us to do this demonstration from 3 remote locations for you tonight. And now I'm going to turn it back over to Brian for a few concluding comments.
Thank you, Howard. In conclusion, I'd like to recap some of the accomplishments of our project. The first thing we did is we studied and analyzed the existing system. And this is useful for us and for Dordt College because if they ever decide to implement this system, they'll have this knowledge at their hands and they'll know what they're working with to begin with. Second, we designed a proposal of a two-way system, and you can kind of see some of the usefulness of that. And if Dordt wanted to go ahead with this system, they would have a design of it that they could use already. And then finally, we demonstrated the feasibility of a feedback system and demonstrated how a two-way cable system works. So are there any, finally I'd like to acknowledge the following people. Dr. Douglas Gore is our team mentor. Ralph Goumet provided a lot of technical information and a lot of equipment. Fred Hahn in the Media Center provided a lot of equipment and a lot of support. And finally, the camera operators that are running the cameras at different locations. So, are there any questions from the audience? Barry?
What was your budget?
Our budget was $500, and that's why we were unable to purchase the more expensive low-frequency modulators.